So, very good evening to everyone, and welcome to the NPTEL's 10th live interactive session on the course Mechanical Behavior of Materials Part 1. The course instructor for this course are Dr. Sashank Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, Shubham Jaiswal. I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in this live interactive session, we will be going to solve some concept related problems based on our weekly content, which will in turn will help you to solve your weekly assignments. So, in today's session, first we will recapitulate what are the things that has been covered in week 10. Then we'll followed by some concept related question, and if the time permits, we'll try to solve the week 10 assignment as well. So let's begin. Am I audible, guys? So, the week 10, we started with the concept known as solid solution strengthening. In week 9, we have seen the precipitation strengthening and dispersion strengthening. So, now in week 10, we have seen the solid solution strengthening. So, what is solid solution strengthening? So, the strengthening due to the addition of the solute atom is called as the solid solution strengthening. This is just a basic definition. Strengthening due to addition of solute atoms is called as solid solution strengthening. Okay, so this is the basic definition of solid solution strengthening. So, as in case of the aging curve of aluminum 4 weight percentage copper, we have seen that when there is means at time t equal to 0, there is some hardness is there. So let me plot. So here we have aging time t, and here we have hardness h. So we have seen some curve like this. Okay, so now here we have seen that some initial hardness, that is H naught, is there. So, and here I have wrote that time, that is alpha SS, that is solid solution strengthening. So there is some contribution of solid solution strengthening towards the H naught. Okay. So means that solution strengthening is somehow contributing to the H naught. So let me write down that also. Okay, when the time t equal to 0, but as the time increases, the other mechanism like precipitation strengthening is also contributing to the hardness of the material. So then what is the difference between the solid solution strengthening and precipitation strengthening? So the precipitates are the they can have the different crystal structure, and they are nothing but a phase. But in solid solution, the crystal structure of the solvent remains the same. Means it will not change. But and the solute that we are talking about, these are nothing but the atoms. So solution the crystal structure of the solvent remains same, but precipitates can have different crystal structure. And second point, that solute are atoms and precipitates are phase. So after this, we have seen the effect of the solute concentration on the strength of the material and as well as the on the ductility of the material. So let me plot. So let's say this is my stress and here I have a strain. So let's say this is the curve for pure metal. Okay, means pure metal. Okay, so now if I add some weight percentage of B or some second element, so with the concentration C1, so it will have some increase in the strength as well as some reduction in the ductility is also been observed. So this is the C1 solute of concentration 1. Okay, so now suppose if I increase the concentration of B, so let's say it is C2. Okay, so this is my UTS here. Okay, so let's say this is the C2 solute of concentration C2 such that C2 is greater than C1. So we have seen that as we increase the solute concentration, the strength increases, but there is a slight reduction in the ductility is been also observed. So I can write that as we increase the solute concentration, the strength increases and ductility decreases. Okay, so this is about the effect of solid concentration on yield strain and ductility. Then we have also seen that the solid solution offers a greater resistance to the dislocation motion than the pure crystal. Here you can see that the pure crystal is having the less strength as compared to that of the after adding the some solid concentration. So now suppose if I plot that is the tensile strength versus the variation in composition as well as the elongation with the variation in composition. So we'll get to graph something like this. Okay. So here I have a tensile strength on y-axis, and here I have some pure A, and then I am adding weight percentage of B, some weight percentage of B. So initially it will have some strength, that is the pure A. So as I increase the concentration, so I will get some slight increase in the strength. Similarly, if I further increase, so I will get a further increase in the strength, and these strengths will keep going on. So we'll get a trend something like this. With increasing the solid concentration, the tensile strength of the material is increasing. Okay. On the other hand, if we plot elongation versus so let's say elongation on this axis. So the pure A will be having the higher elongation. Okay. So as I increase the solid concentration, the elongation will start to decrease. So we will get a trend something like this. That is the with increasing in the solid concentration, the elongation is decreasing. Okay. So these are the things we have seen. Then we have seen what are the different types of solid solution that exist. Okay. So okay, let me end this section here itself. Okay. So solid solution. So we have two different types of solid solution. One is the substitutional solid solution, in which the solid atoms replaces the solvent atoms, like in the case of copper and nickel. And the second one is the interstitial solid solution, in which the solid atoms occupies the voids or the spaces between the or the interstitial position between the atoms. So we have two categories. One is substitutional solid solution, interstitial solid solution. So in substitutional, what happens? The solid atoms replaces solvent atoms, while as in case of interstitial, the solid atoms occupies the voids or interstitial position. So for example, so here we have copper in nickel, and here we have example carbon in iron. Okay, so if I draw, so let's say okay, so let me mark here. Let's say this is my A atom. Sorry. Let's say this is my A atom, and let's say this is my B atom. Okay, so In substitutional, so what we have seen that the solute atoms replaces the solvent atom. Okay. So these all are of the same size. Okay. So here you can see that here at this position, the black one, the solute atoms has been replaced by the the solvent atom has been replaced by the solute atom, that is the B atom. Okay, so this is B atom, and all these are A atoms. Okay, so on the other hand, in the interstitial, so here you can see that all the A atoms are at their position, but the B atom is occupying the space in between that of the B atom is occupying the some interstitial position, or the it is sitting in the voids. Okay, so this is interstitial position. Okay, so these are the things we have seen about the solute solution. Now after that we have seen that the distortion in the lattice causing due to the solute atoms. So like how this addition of this solute atoms can distort the lattice. So distortion in lattice due to solute atom. So let me draw first. Okay. So that let's say this is my some B atom, and now I am drawing my some A atoms. Sorry, I'm not good with the drawing. Okay. So please bear with me. So here the solute atoms, that is the B atom, is sitting in the void. So it is somehow distorted the lattice. Okay, so the distortion is something like this. Okay, so the distortion here is non-spherical. So what we can say that the interstitial solute atoms leads to the non-spherical distortion field. Okay, so either it is in tetragonal void or octahedral void. So on the other hand, if I draw the solute atom for a substitutional case, so let's say Sorry. Let's say this is my B atom. Okay, in one case it is large and one case it is small. Okay, let's consider. So here if you see, okay, so the distortion, like the distortion you can see, okay, it is same everywhere. That is, the substitutional solute atoms lead to a spherical distortion field. Okay, so this is the case when the solute atoms is larger than the A atom. And what will happen if it is smaller than the solute atom, solvent atom? So So here you can see that the substitutional solid atoms are leading to the spherical distortion field. So let's see, this is my black one, is my B atom. So in case of interstitial solute atom leads to a non-spherical distortion field, whereas in case of the substitutional solute atom leads to a spherical distortion field. Okay, so it will lead to some spherical and non-spherical distortion field. Okay, whether it depending on it is whether it is interstitial or substitutional. So these atoms are creating some stress field around the solid atoms. Okay, so this stress field around the solid atoms will interact with the stress fields around the dislocation, and in this way they will hinder their motion, and this will lead in the increasing the strength of the material. So let me write down that as well. Lead to increase in strength. Okay, so this is how the solute atoms increases the strength of the material. So after that, we have seen what are the factors that affect the solute solution strengthening. So, factors affecting the solute solution factors affecting the solute solution strengthening. So what are the factors? Can anyone tell? Okay. So in this we have seen the one first factor, that is the size of solute atoms. Okay. So in that we have seen with the different graph, with the help of graph, that the more the size difference is there, the higher is the strengthening effect has been observed. Similarly, the elastic modulus of the solute. So higher the modulus of the solute atom, so higher is the strengthening effect has been observed. Similarly, the solid concentration. So increase in the solid concentration resulted in the increase in the strengthening of the material. So let me write down all three one by one. So the size of solute atom. So more the size difference, higher is the strengthening effect. Okay. The second, that is the elastic modulus of solute atom. Elastic modulus of solute. So higher the modulus, higher is the strength. And the third thing, that is the solute concentration. So in solute concentration, we have seen that increase in the solute concentration increases in the strength. So, as in the third point, we have said that the solute concentration, that is, if we increase the solute concentration, the strength will be increasing. So, can we keep on increasing the solute concentration? So, no, we can't keep adding the solute in the solvent, as there is some solubility limit, and after which it will start forming the some second phases. So, up to particular limit or solubility limit only we can add a solute atom. So let me write down it as a note. Okay. As there is some solubility limit, after which it starts forming second Okay. And also we have seen that for the same size difference, the smaller atoms give the greater strengthening effect. For the size difference, the smaller atoms gives greater strengthening effect. Okay, so these are the things we have covered in the factors that are affecting the solid solution strengthening. So after this, we have seen the concept that distortion in the lattice due to dislocation. So distortion in the lattice due to dislocation. So for the edge dislocation, we can write stress matrix as sigma x, sigma xy 0, sigma y, sigma yy 0, 0, 0, sigma zz. So here for the edge dislocation, so both shear and tensile or compressive stress fields are present, and both the distortional and dilational component are present. Means hydrostatic components are also present in case of the edge dislocation. So similarly, if we write for the screw dislocation, so we can see so in case of the screw, only the shear stress field is there, no hydrostatic components are there. So it means only distortional components are present. So for edge, so and here in the case of screw, only shear stress field and only distortional component. So based on this, we have determined how the substitutional solid atoms interacts with the edge and screw dislocation, and how the interstitial solid atoms interact with the edge and screw. So if I write like, let's say this is edge, screw, and here suppose I have substitutional and interstitial. So let me make a box here so that you can so the substitutional atom interacts with the edge only, and it will not interact with the screw. While the interstitial will interact with the edge as well as the screw. So from here we can say that the interstitial solute atoms will give higher hardening effect as compared to that of the substitutional atoms. So let me write down that as well. As compared to substitutional atoms. Okay, so that too in per unit concentration. So this is about the distortion in the lattice due to dislocation. So now we need to know the how this impurity atoms or the we can say that solute atoms sit with respect to that of our dislocation. So let me draw the dislocation for you first. So let's say this is my slip plane and this is my dislocation. So we have seen that here let me draw for you. Let's say this is my dislocation. Okay. So the region above the dislocation is in the compression. So let me write down. Okay. And the region below the dislocation is in tension. And in between we have the region of shear as well. Let me make it colorful. So this is the compressive region and this is the tension, and here on the upper side we have the compression, and we have some shear region as well. Okay. So what will happen? So the impurity atoms are attracted to the dislocation so that it can reduce the overall strain energy. So also we can say that it will partially cancel the strain in the lattice, and by which it will minimize the strain energy. So the impurity atoms will always try to sit towards that of the means near to that of the dislocation. So here, if the atoms is interstitial, okay, so it will sit near to that of our just beneath that of our edge dislocation. So this is interstitial atom. So if the atom is smaller than the so is smaller than the or solvent atom, so it will try to sit in the compression region. So let's see. Substitutional atom smaller than solvent, and if it is larger than the solvent atom, so it will sit in the tensile region. So, let me change the color, so I will use red here. Substitutional atom larger than solvent. So I can write that impurity atoms are attracted to dislocation to reduce the overall strain energy, or it will partially cancels the strain in the lattice. So these are the things we have seen in the how this solid atoms will sit respect to that of our dislocation. So let me write down one more thing, that is the interspatial atoms mostly go below dislocation line. Okay. So these are the things we have seen about the position of the solute atoms. So after that we have seen the concept known as quartal atmosphere and yield point phenomena in medium carbon 3. So quartal So let's say you have a dislocation here and some solid atoms are sitting near to this one. Let's say these are the carbon or nitrogen atoms in. So this of atmosphere, that is the near to the dislocation, some solid atoms are continuously there. So this type of is known as quartal atmosphere. So this concept has been introduced by Cottrell. So after that we have seen the yield point phenomena in medium carbon steel. Okay. If I plot for the stress strength or for the pure aluminium, means pure polycrystalline aluminium, so I will get a curve something like this. Okay, so here I have the strain and stress. Okay, okay. So here you can see that I am having yield point, and there is no fluctuations are there, and the yield point is visible. Okay, so if I draw the same, if I do the tensile test for the medium carbon steel, so I will get a curve something like this. Okay, this is stress and strain. Okay, so first we will get a elastic region. Okay, then there is a drop in the strength, then we will see some fluctuations, and then we'll see the remaining curve. Okay, so this is my fracture point, this is my UTS, this is my upper yield point, this is lower yield point. So in this case we are getting two different yield points. So one is the upper yield point. So here we can say that as the stress goes up, so the dislocation in a set of favorably oriented grains. Okay, so suppose if, let me draw the sketch for you. So if I am doing a tensile testing, so there might be some grains which are favorably oriented. Okay, and they are freed from the quartal atmosphere. So to get it free from the quartal atmosphere, it will require the higher stress value. So, and after that, there will be a burst of plastic staining will be taking place in the narrow band. So that narrow band is known as the Luder's band. So as I am in this applying the load to the material, the stress goes up, so that the dislocation in the favorably set of oriented grains will be freed from there. So that's why we'll get a upper yield point. So So the dislocation in a set of favorably oriented grains are freed from the quartal atmosphere. So it will require a higher stress. So a burst of plastic straining takes place in narrow band also known as Luders band. Okay. Luders band. Okay. So this is how we get the upper yield point. Then why do we get the lower yield point? So in the testing we will try to maintain the constant strain rate. So the constant strain rate we'll try to maintain during the testing. So the strain rate is given by epsilon dot b rho v. So here rho is the dislocation density, v is the velocity of dislocation, and epsilon dot is the strain rate. Okay, and also this velocity v is directly proportional to the shear stress tau. So in a band region, so what will happen? So in a band region, so what will happen? So in a band region, the dislocation density will increase. So rho will increase. So it will try to increase the strain rate. So, but we are maintaining the constant strain rate, so we should decrease. So if V is decreasing, it means the stress is also decreasing. So why it is decreasing? To maintain a strain rate constant. So what is the lower yield point then? The reduction in the stress to maintain the constant strain rate. So that point is known as the lower yield point. Lower yield point. Okay. So these are the things we have seen about the yield point phenomena in equatorial atmosphere. Then after that, we went to see the new concept, we have seen the new concept known as grain boundary. Grain boundary strengthening. So, what is grain boundary strengthening? So, this strengthening effect is observed due to the hindrance in the dislocation motion due to the presence of the grain boundary. So that's why it is known as the grain boundary strengthening. Hindrance in dislocation motion due to presence of grain boundary. Okay. So how it will strengthen the material? So let's say here I have some grain 1, so let's say here I have one dislocation. Let's say here I have another dislocation. Okay, so and I have another grain on this side. Okay, let's say so this is my grain boundary. Okay, so grain boundary, this is my grain 1 and this is my, let's say, grain 2. So here we can say that we can see that the orientation of the grain is changing from grain 1 to grain 2. Grain 1 to grain 2. So here, as you can see that in the orange color, as the dislocation is passing into grain 2 from grain 1, it will have to change its direction of motion because due to the crystallographic misorientation. And similarly, the atomic disorder within the grain boundary region will restrict in a discontinuity of a slip plane from the one grain to the another grain. So here, if it is the slip plane, so in this grain, so it will need to move to this slip plane. Okay, so this hindrance will result in the strengthening of the material. So let me write down. Strengthening occurs due to first or dislocation passing into grain 2 from grain 1 will have to change its direction of motion. So why is it so? It's due to the crystallographic misorientation. And the second thing is that the atomic disorder within grain boundary region will result in a discontinuity of slip length from one grain to another. One grain to another. So this is about the strengthening in the strengthening due to the grain boundary. So as these dislocations are not able to traverse through the grain boundary, so what will happen? It will pile up at the grain boundary. Pile up of dislocation. So let's say this is my okay. First, let me write down how the piling up of dislocation is being taking place. So a dislocation are not able to traverse through obstacles, or in our case it is grain boundary. So it will result in the pile up of dislocation. So let's say this is my grain boundary. So let's say one dislocation is there. Okay. So it is not traversing through the grain boundary. Okay, it is at the grain boundary. So here we have applied some shear stress tau, and here I have some dislocation source which is continuously emitting a dislocation. So what will happen? So another dislocations will come here. So the stress field of this zero dislocation will try to offer the moment of first dislocation. So it will make it equilibrium somewhere here. This is first dislocation, this is zeroth. So again, the second dislocation is coming. So it will also restrict its motion here. That is 2. So the distance between these dislocations is given as x10. Let's say this is x21. So now we know that the force on a dislocation is given by Fx equal to gb square 2 pi 1 minus nu into x upon x square minus y square upon x square plus y square whole square. As all these dislocations are on the slim plane, so the y equal to, so y is 0. So we'll get the final equation as gb square 2 pi 1 minus mu into 1 upon x. So in this pile up, the each dislocation is under equilibrium because of two things. One is the effect of applied stress, that is the tau, and the second one is the stresses due to the other dislocation in the pile up. Means this 0 will be exerting some stresses on 1 or 2. Similarly, this 2 is exerting on 1 and 0, and similarly this 2 and 1 will be exerting on the 0. So each dislocation in a pile up is under equilibrium. So each dislocation in this pile up is under equilibrium. So one is due to the effect of applied stress tau. Second one is the stress due to other dislocation pile up. So what does it mean? So the net resulting force acting on the dislocation should be 0. So therefore the resulting force acting on the ith dislocation should be 0. So it means that is the force exerted due to the applied shear stress is tau b minus summation of j equal 0 to n gb square upon 2 pi 1 minus mu into 1 upon xi minus xj should be 0, and here I should not be equal to j. So this is the resulting force acting on the ith dislocation. So as all these dislocations will be exerting a stress and the leading dislocation, means this one 0. Okay, so this 2 will be applying some stress on the 0. Similarly, the 1 will be applying some stress on the 0. So what it is doing? So it is applying some stress at the leading dislocation, and that the stress on the leading dislocation is given by the number of the dislocation in a pile up multiplied by the applied result shear stress. So the tau star, that is stress at leading dislocation, is given by tau equal to n into tau a, where tau a is nothing but the applied result shear stress, and this n is nothing but the number of dislocations in a pile up. So can there be a more numbers of dislocation, means infinite number of dislocation in a pile up? So no, as these dislocations are exerting some stress, so what will happen? It will exert some back stress. Okay, so this dislocation will try to exert some back stress in this direction. Okay, in the direction of Frank Reed source. So after a particular length after a particular number of dislocation, so it will stop generating the dislocation. So there are some limited number of dislocations in there. So it means there is a certain length is there for a pile up. So this is due to the back stress generated by all the dislocation in the pile up. So the number of dislocation in pile up is given by n equal to L pi tau A by alpha GB, where tau A is nothing but a resolved shear stress, alpha is geometrical constant, depends on the type of this dislocation. So it is equal to 1 for screw dislocation, and it is equal to 1 minus mu for H dislocation, where B is nothing but our Burgess vector and L is nothing but the length of pipe. So when the source of our dislocation lies in the center of the grain, so what we can say that when source lies in center of grain, it means the L will be equal to D by 2. So if I put the value of this L by L in the equation of number of dislocations in a pile-up, so I will get D by 2 equal to N alpha GB by pi into tau A. So this is the equation when the source lies in the center of a grain. So now after that, sorry guys, so after that we have seen the concept that is the critical stress required to overcome a grain boundary obstacle, that is tau C. Means what is this stress is nothing but the stress dislocation in a pile-up will be able to move the grain boundary if we exceed the value of TC. So okay, so it is nothing but that the highest means the stress that will be acting on the leading edge dislocation should be greater than the value of tau C, which means N into tau A should be greater than or equal to tau C. So now if I put the value of N here and considering the dislocations lies in the center of the grain, so I will get the equation something like this, that is D by 2 into pi tau A upon alpha GB into tau A should be greater than or equal to tau C. It means the tau A should be greater than or equal to 2 alpha GB tau C by pi square root into d to the power minus 1 by 2. So here if we see, this much stress will be required to overcome the grain boundary obstacle, and as well as there will be some component of the uh, account of friction stress will also be there. So if we consider that in account, so tau a should be greater than or equal to tau naught plus this term is nothing but the constant k into d to the power minus 1 by 2. So this term is k. So and this tau naught is due to it is added to take into account the friction stress needed to move a dislocation. Okay, so after this we have seen that some Hall-Page theory and Cottrell theory. So what does Hall-Page theory says that the dislocation can burst through a grain boundary. So the Hall-Page said that the dislocation can burst through a grain boundary and it is valid for a large number of dislocations in a pylon. And the second theory that is given by the Cottrell theory. So what is suggested that it is virtually impossible for a dislocation to burst through the grain boundary. So rather it will try to produce a dislocation in the second grain due to the stress concentration produced by the pileup on the grain boundary. So in Cottrell theory, so what he suggested that suppose these two grains are there, so it is virtually impossible for a dislocation to burst through the grain boundary. So what will it will do? It will create a dislocation solely in the adjacent grain. Okay. So and suppose this is distance r0, and this is how the dislocation in the adjacent grain will be generated. So in this case, the tau a is great. It should be greater than or equal to tau naught plus 2 tau c r to the power 1 by 2 into d to the power minus 1 by 2. This is about the Cottrell theory. Then after that, we have seen the Hall-Page relation. So this Hall-Page relation gives the relation between the yield strength of the material and to that of the grain size. So it is given by sigma y equal to sigma naught plus k to the power k divided by root d. So here sigma y is nothing but a yield strength of polycrystalline material. Sigma naught is nothing but a friction stress for dislocation moment, where d is nothing but the grain size. So here from this equation we can say that as the grain size decreases, the yield strength of the material increases. So this type of strengthening, grain boundary type of strengthening, it is used where the precipitation strengthening, dispersion strengthening uh, are or the solid solution strengthening are not suitable. Like in case of the pure metal material, so we can do this type of strengthening. So if I plot this Hall page equation, so this is in the form of y is equal to mx plus c. So here I will be having some sigma y, and here I will be having the 1 upon root d. So if I plot, so I will get something like this. So the slope of this line is nothing but our k, and the intercept is nothing but sigma naught. Okay, so this is all about the our week 10 content. So now we'll go towards solving our some concept related problems. So here is the first question. So the yield strength of a low carbon steel depends on its grain size. Following data have been reported. So they have given the two grain size and their corresponding yield strength. So they are asking us to estimate the yield strength of the same steel treated to give the grain size of 0.0156 mm. So please try to solve it, guys. So please try to solve it, guys. It's very, you just need to use the Hall page relation because they have given the grain size and yield strength. So the Hall page relation gives the relation between the yield strength and the grain size of the material. So did you got the answer? Okay, we will solve it together. Okay. So what they have given? So they have given that sigma y1 is equal to 205 megapascal when the grain size is of 0.025 mm. They have given the second yield strength of 125 megapascal when the grain size is of 0.15 mm. So they are asking what will be the grain size, what will be the yield strength if the grain size is how much? 0.0156 mm. So we know the Hall page relation. That is sigma y equal to sigma naught plus k by root p. So here we have the value of sigma y and d. We don't know the value of sigma naught and k. So how we can find out? So here they have given the two yield strength corresponding to two different grain sizes. So we can use and we can solve that equation simultaneously, and we'll get the value of sigma naught and k. So first, if I consider the sigma y1, so how much it is? 205 equal to sigma naught plus k upon root d. Let's convert it into the meter. So it is 0.025 into 10 to the power minus 3. So it should be equal to 205 equal to sigma naught plus 200 k. Let's say this is equation 1. Now the second one we have 125 megapascal equal to sigma naught plus k upon root d is how much? 0.15 into 10 to the power minus 3. So it is 125 equal to sigma naught plus how much this value? So it's coming out to be 81.65 k. Let's say this is equation 2. So now solve this equation at 1 and 2. So solving equation 1 and 2 will result in sigma naught comes out to be how much it is? 69.81 megapascal, and the k value comes out to be 0.0676 megapascal into root meter. So now we have the value of sigma naught and k. So and also we have the value of d. So we can find out the value of sigma y3. So now sigma y equal to sigma naught plus k by root d. Sigma naught is how much? Sigma y is equal to 69.81 plus 0.0676 upon root d. So now we need to find out sigma y equal to how much if d is equal to 0.0156 mm. So now put the value of d in above equation, we'll get the value of sigma y. Sigma y equal to 69.81 plus 0. Sorry guys, here only 10 is there. 0.676. So 0.676 divided by we have 0.0156 into 10 to the power minus 3. So the sigma y comes out to be how much? So it comes out to be 241 megapascal. So this is our answer. So here you can see that as the grain size is increasing, okay, so here the grain size has increased, so yield strength has decreased. So here we have as the grain size has decreased, the yield strength has increased. So now here you can see that they have asked us to calculate 0.0156 mm. So it is less than 0.025 mm. So the yield strength value should comes out to be greater than 205. So if you have a MCQ question, so by just observation you can also answer. Okay. So no need to go for such calculation. So just by the observation and knowing the relation between the yield strength and grain size, you can easily answer the MCQ question. Okay. So now we'll move towards our second problem. So they have asked us, the second problem is like that. Consider an aluminum polycrystal with a grain size of 10 micrometer. If a dislocation source at the center of grain emits dislocation under an applied shear stress of 50 megapascal, that pile up at the grain boundaries, what is the stress experienced by the grain boundary? So take G equal to 26 GP and B equal to 0.3 nanometer. So for your better understanding, I will draw the sketch. So they are saying, let's say this is our one grain. Okay, so somewhere here we have a source. Okay, so and here we have a dislocation pile up. Okay, let's say we have a dislocation pile up and we have applied some shear stress tau A. So they are asking us to. So what they are asking us? They are asking us to calculate the stress experienced by the grain boundary. So they are asking us how much stress is being experienced by the grain boundary. So now you can think which equation we should use and try to answer it. Please try to answer it, guys. Any guesses, guys? Okay, first we'll write down the given data. So they are saying consider an aluminum polycrystal with a grain size of 10 micrometer. So grain size is nothing but D equal to 10 micrometer. Now they are saying that if the dislocation source is at the center of grain, so dislocation source is center of grain. So in that case, the length of pileup is given by L is equal to D by 2. Why? Dislocation at center of grain. Now after that we have under an applied shear stress. So they have given the applied shear stress of 50 MPa. So this is applied shear stress. So tau A is equal to 50 MPa. Now what they are saying, the grain boundary, what is the stress experienced by the grain boundary, and they have given the value of G and B. So this is G equal to 26 GPa and B equal to 0.3 nanometer. So now what they are asking us to calculate the stress experienced by the grain boundary. So how much stress will be experienced by this grain boundary? So it will be same as that of the. So it will be same as that of the of what? So it will be same as that of the stress at the leading edge dislocation. So this is leading dislocation. So the stress will be on this will be tau star is equal to n into tau a. So this much tau star amount of stress will be experienced by the grain boundary because that much.
நான் விழுந்துட்டேன். அதுல அவர் நல்லா அமுக்கிங்கெல்லாம் அமுக்கி பார்த்தாரு. வேற ஒண்ணும் இல்ல. நீங்க ஒரு ஆயின்மெண்ட் எழுதியிருக்காரு, அதை போடுங்க. வத்திட்டு நல்லா வத்திட்டு அவர் நல்லா அமுக்கப்ப நான் திடீர்னு.
So this much stress will be experienced by that of our grain boundary. So we know that n is given by L pi tau a upon alpha GB, and if we put the value of L as d by 2, so we'll get a n value as d pi tau a by 2 alpha GB. Okay. So here we don't know the value of alpha. So whether it is the screw dislocation or edge dislocation. So means they have not given either whether it is the screw or edge dislocation. So we'll calculate for the both. So alpha equal to 1 for screw dislocation and alpha equal to 1 minus mu for edge dislocation. So and we will assume nu to be 0.3. So if I calculate for screw, so tau star equal to n into tau a. So n is how much? D pi upon 2 alpha GB into this tau a, and tau a will become tau a square. Okay. So and here the alpha value is nothing but 1. Okay. So I can calculate tau star as D is how much? D is 10 micrometer. And 10 by 2 is 10 into 10 to the power minus 6 into pi into we have tau, that is 50 into 10 to the power 6 whole square, divided by what we have 2 into G. G is how much? G is 26 GPa. Let's convert it into the Pascal. We'll get 10 to the power 9. And B is how much? It is 0.3 nanometer. Let's convert it into the meter. So 0.3 into 10 to the power minus 9. So we'll get tau star for screw dislocation to be how much it is coming? So it is coming out to be 5034.6 megapascal. So now similarly calculate for edge dislocation. So did you got the answer for edge component? Okay. So for each component, we have same equation, tau star equal to d pi by 2. Here we will be having the value of alpha, that is 1 minus mu into gb into tau square. So if you put all these value, so we'll get tau star come out to be 7192.29 megapascal. So this is for edge dislocation. So any doubt in this question? Okay, so let's move towards our next question. So here the question is like that. The tantalum polycrystal is deformed at a strain rate of 10 per second. So assume that dislocation cannot cross grain boundaries, given that B is equal to 0.2 nanometer and dislocation density is 10 to the power 4, 10 to the power 14 per meter square. So they are asking us to calculate the velocity at which dislocation will. It's just 30-second questions. Please try to answer it. It will not take much time. Just one simple equation you need to use and you will get the answer. So let's first write down what are the things that have been given. So they have given us the strain rate as 10 per second. Then we have the Burgess vector as 0.2 nanometer, and the dislocation density, that is rho, is given as 10 to the power 14 per meter square. So we know the relation between the strain rate and the velocity, as we have already discussed it in the quick recapitulation. So it is given by epsilon dot equal to rho into B into V. So V should be rho into, sorry. So the velocity of dislocation is nothing but epsilon dot upon rho into B. So epsilon is 10. B is, let's convert it into the meter. So B is how much? 0.2 into 10 to the power minus 9 meter. Now we have given G. So it is 10 to the power 14. So you will get a V value somewhere around 5 into 10 to the power minus 4 meter per second. And if you convert it into the mm, you will get it as 0.5 mm per second. So this is your velocity of dislocation, with which dislocation will move. So okay, this was just simple questions. We'll move towards next question. So they have given, in an FCC material, a moving edge dislocation is pinned by an obstacle A shear stress of 150 megapascal is applied to drive another dislocation with same Burgers vector and moving in the identical plane. So approaching the first dislocation given, they have given the value of E nu and lattice parameter, and they are asking us to calculate the equilibrium separation between the two dislocations. So please try to answer it, guys. Please try to answer it, guys. Okay, let's see. So first we'll write down the what are the things as given. So the shear stress is given, that is tau equal to 150 MPa. Then they have given E as 210 GPa, nu as 0.3, and the lattice parameter is given as 0.35295 nanometer. So we'll try to draw the diagram first. Okay. So what they are saying, so it is a FCC material. So the one edge dislocation is moving. Okay, and it is pinned by an obstacle. Let's say, suppose here I have an obstacle. Okay, and one dislocation has been pinned here. Okay, edge dislocation. Okay, let's say this is our first dislocation. Okay, so a shear stress of 150 megapascal is applied to drive another dislocation. It means some other dislocation is been moving in there. Okay, with the same Burgers vector. It means the Burgers vector of 1 is same as Burgers vector of 2, and they are moving in identical plane. So in this plane, somewhere here the dislocation 2 is moving. Okay, so and both have the same Burgers vector. So this is the same plane, and it is approaching towards the first dislocation. So it is moving towards the first dislocation. So they are asking at what distance that dislocation 2 will be in the equilibrium position. So they are asking us to calculate this distance x at which these two dislocations will be in equilibrium. So and these second dislocations is being applied with the shear stress tau. So this is the question of dislocation pylon. So we know if the dislocations are in equilibrium in the pylon, we know that their force exerting on them should be equal to 0. That is tau b minus summation j equal to 0 to n gb square 2 pi 1 minus nu into 1 upon xi minus xj should be equal to 0, such that I is not equal to j. So in this case, we have only one dislocation. So our equation will become like, so I will write here, okay, tau b minus gb square 2 pi 1 minus nu into xi minus xj. The distance between these two dislocation is nothing but is this 1 upon x equal to 0. Okay, so now what they are asking us to find out the value of x. So if I write the equation in the form so that if I rearrange, so I will get something like this, that is gb square 2 pi 1 minus nu into 1 upon tau into b. Okay. So in this equation, we know the value of g, we know the value of pi, we know the value of mu, we know the value of tau. So we need to find out the value of x, but we don't know the value of b. So how do you calculate the value of b? That is the Burgess vector. So please revise all old concept from the week 7, week 8, and you will get the answer. So in last week also similar type of question, like in which the Burgess vector was not given. So we used that concept and we calculated the value of Burgess vector. Did you got any hint? Okay, so I will give you the hint. So what is the slip plane and slip direction in case of FCC? So slip plane is 111 and slip direction is 110. So we know for FCC the Burgess vector is of the type a by 2 1 1 0. Is it not? So if I calculate the magnitude, it comes out to be a by root 2. So they have given us the value of a. So if I put 0.35, sorry, it is 0.35295 divided by root 2. So the Burgess vector value comes out to be 0.24957 nanometer. So this is how you got the value of Burgess vector. So now you have all the value, you just need to find out the value of x. So please calculate it, guys, and tell me the answer. So let's say this is equation 1. So from equation 1, x equal to g is how much? So also we don't know the value of g. So how do you calculate the value of g? Okay, so the value of g is also not given. So how do you calculate? So we know the relation, that is g is equal to e upon 2 1 plus mu. So e is how much? E is given as 210 upon 2 into 1 plus 0.3. So we'll get the value of G. So it comes out to be how much? 80.77 GPa. So now we have all the values, that is G, B, tau and nu. We can easily find out the distance. So if I put, so from equation 1, x equal to 80.77 into 10 to the power 9 into 0.24957 into 10 to the power minus 9 whole square divided by 2 into pi into 1 minus 0.3 into tau is how much? 150 into 10 to the power 6 into Burgess vector is how much? It is 0.24957 into 10 to the power minus 9. So now please tell me the answer of x. So x is how much? So x comes out to be 30.55 nano. So is this clear? How we have calculated the equilibrium separation distance between the two dislocation? So first we draw the first we wrote down the equation. So in that we had the two unknown. One was the Burgess vector and one was the G, shear modulus. So the Burgess vector was not given, but for the FCC we know the Burgess vector is a by 2 in a by 2 110 type. So we calculate the Burgess vector using that concept. So now so the G value was not given, but the new value was given. So we can use the relation G is equal to E upon 2 1 plus mu. From that we will get the G. So now we had all the values. So we put it in the equation 1 and we finally got our answer. So any doubt in these questions or till any or till this point? Anyone? Okay. So if no doubts are there, so we will end our today's session here itself. So one more chance. If any doubts are there, just please ask, or I will end today's session here itself. So no doubts. So I will end today's session here itself. Thank you everyone for attending. Okay, bye guys. We'll meet in the next week.